In this video, we're going to have a look at inverse functions purely from the context of transformations. So what we can see here is that every point xy maps onto yx. So what I'm saying is that every coordinate xy maps onto yx. So that's what happens to each coordinate on the graph. It's why oftentimes when you think of inverse functions, you hear the phrase swap x and y. But what does this look like as a function? Well, we would say suppose we had a function f such that y equaled f of x. To find the inverse, we would say the inverse of f is such that x equals f of y. So that's really important to notate that. If you are doing something like swapping x and y, but you've never ever introduced y, the question itself just said f of x, you'll need to introduce y as a variable. And this is the way we do it. We're saying let our function f be such that y equals f of x. And so our inverse function would be such that, that's what that colon means, such that x equals f of y. So really when I'm doing this, I'm saying swap x and y. Now the final way we might consider this is through a matrix transform. Usually we would have our dilation matrix looking something like 1, 0, 0, 1, and we would multiply that by x and y. Well, the way to represent that it is an inverse transformation, or find the inverse function as a transformation, is to say 0, 1, 1, 0. Now let's imagine, what does that do? If that was my transformation, say x dash y dash, what would that do? Well, the top line would be 0 times x plus 1 times y. So 0x plus y. And then on the bottom row, I'd have 1 times x plus 0 times y. And so what I end up with is yx, sorry, that should be a matrix bracket, yx is equal to new x and new y. And so that's how I'd swap it. So the reason for saying this, will clear a bit of room. Reason for saying this is that we can represent this transformation as 0, 1, 1, 0. And that would be times xy. So there's a couple of ways we can do this. Now, you might be curious and thinking, why would I even want to find the inverse function? And why would it be considered a transformation if I'm swapping x or y? And the reason is, imagine that I had one graph, which is this blue line here, f. When we're swapping x and y, when we're finding the inverse function, what we're actually doing is reflecting about the line y equals x. So rather than reflecting about y or x, we're reflecting about the diagonal line y equals x. So think of this like a reflection along the leading diagonal. Now, there are some very important properties here to consider. As we mentioned, any point that lies on the first line will have its x and y swapped in the second line. So if this line y equals f of x, if the point 1, 2 lied on this line, so if this point here happened to be 1, 2, then what I know must be the case is that on the line y equals inverse of x, so over here, there's a corresponding point 2, 1. So I can find any critical point on the inverse just by swapping the critical point on the line y equals f of x. The other implication here that's important to remember is that the domain of the inverse is equal to range of the original function. So because we're swapping x and y, we're also swapping their domains and ranges. Likewise, the range of the inverse is the domain of f of the original. So these are two really important things to consider, and will usually be asked of you not only find the inverse function, but also state its domain and range. To do that, look at the original function and see if you can just swap its domains and range. Now, the other critical thing to remember is that only one-to-one functions have an inverse. So we'll just try and highlight that there. Only one-to-one functions have an inverse. So if I had something like a parabola, and we can draw that up really quickly, this parabola, as it stands, does not have an inverse function. And it's because it's not one-to-one. Now remember, one-to-one means that if I drew a horizontal line like this, I should only cross the graph once. So how would we make this a one-to-one function? Well, for a parabola, we could restrict at the turning point. So here, if my turning point happened to be 1, 2, and that was the graph of the parabola, then my inverse function would have the point 2, 1. And it would shoot off that way. So not only am I swapping points, I'm also remembering that the domains and ranges swap, and also remembering that for an inverse function to even exist, the original one had to be one-to-one. Now, you can see here that in this instance, we have a point of intersection. So how would I find that point of intersection? Well, there's 3 different ways. Like anything, if I want to find the point of intersection between two graphs, I could let one graph equal the other. But that can often be hard. And quite usefully with inverse functions, because it's a reflection along the line y equals x here, I can also find the point of intersection by letting the first graph equal x and then solving, or letting the second graph, the inverse, equal x and then solving. So there's a couple of ways I can go about doing that. So there's a lot of information here. Let's do a quick recap and then we'll put it into practice. So, inverse functions are defined as every point on the first graph swaps on the second graph. We can find them by swapping y and x, so I can find them by swapping my x and y, but in order to do that, I need to make sure that I'm writing out this statement. So that's always pretty important. I could also see this in a matrix equation by having my leading diagonal become 1s instead of 0s. Remember that the shape of the curve will be reflected about the line y equals x. And we can see that each point on the first graph would swap to exist on the second. In order to find the domain of the inverse is equal to the range of the first. And in order to find the range of the inverse, well, that's just the domain of the first. So because we're swapping x and y, we're also swapping domains and ranges. Finally, only one-to-one functions can have an inverse. So that's a really important restriction to make. And so if you are trying to find the inverse graph, you may have to restrict it first. If you want to find the point of intersection, you can let one graph equal x, the other graph equal x, or let them equal each other. But it's strongly recommended that you just let the graphs equal x. That's usually a much easier equation to solve. So in example 1, we're asked to sketch the graph y equals x squared minus 2x minus 3. So let's quickly have a look at how we do that now. We'll need an axis, so I'll quickly rule that up. There we go. And we'll need to think, what is our turning point? So the turning point will always occur, the axis of symmetry, you might have heard this, or the x component of the turning point, will always occur at negative b over 2a. So that's negative negative 2, that's going to be positive 2, over 2, which is equal to 1. Now in order to find the y component of the turning point, all I have to do is sub in that 1 for x. So I've got 1 squared minus 2 times 1 minus 3. And that works out to be 1, take away 2, take away 3, so it's negative 4. The turning point is equal to 1, negative 4. To find the y-intercept, I just let x equal 0. So y-intercept is equal to 0, take away 2 times 0, minus 3. And that's just negative 3. So that gives me some indication of what my shape will look like. I've got a point here, 1, negative 4. It's a positive parabola. And the intercept is 0, 3, or negative 3. Now to find the x-intercepts, I need to let y equal 0. So x squared minus 2x minus 3 equals 0. The factors of negative 3 that add up to negative 2 are negative 3 and 1. And so I've got x minus 3, x plus 1 equals 0. That is, my x-intercepts, they're going to be negative 1 and 3. So that's negative 1, 0, and 3, 0. Now we're asked on the same set of axes, sketch the graph of the inverse. Well, I know that the inverse occurs at the diagonal. Now if it is the line y equals x, then it will be on this 45 degrees. So to help me out, I can probably just draw a dotted line and call that dotted line y equals x. And if I rotate this image, instead of being a U, it's kind of going to look a bit like a C. And so my graph looks a little bit like this. Now I'm not too sure about the shape, so let's see if I can put into practice my understanding in order to help me out. 1, negative 4 will become negative 4, 1 because I'm swapping x and y. So this turning point will also be a critical point, but it'll be negative 4, 1. So that's down here and there. We'll call it negative 4, 1. The x-intercepts, 3, 0, and negative 1, 0, now become 0, negative 1, so I might put that there, and 0, 3, which might be up here. My old x-intercepts, my old y-intercept of 0, negative 3 is now going to be an x-intercept, negative 3, 0. So you can see that I get this shape. Let's just make that my intercept. So it's quite busy, and I apologise for that image. We might draw it nicely in a second. But I'm using the fact that I can swap my x and y in order to help me do the shape. So I'm going to draw that a little bit nicer in the space below, and then we'll revisit this question in a moment. We can see our graph for y equals f of x, and I might as well say there's x and y, and we know that negative 1, 0 will become 0, negative 1. 3, 0 will become 0, 3. So there's my 0, 3, and might just put it in here, 0, negative 1. My 1, negative 4 needs to become negative 4, 1. And that gives me a good general shape. My 0, negative 3 is going to be negative 3, 0. So you can see that we get this kind of C-type shape. and this is really ultra busy. And the reason is, as I mentioned previously, the parabola is not one-to-one. And so calling this y equals f of x is not actually going to help me that much. So let's revisit the rest of the question, and we can explain why. You can see that we've completed part A and B below. That was to sketch the graph, and on the same set of axes, sketch the graph of the inverse. Now we're asked to state whether the relations are functions. And we can see that while y equals f of x, while that be a function, the second graph is just a relation, because it fails the vertical line test. Now, if we were asked to give the domain and range for each of the graphs, let's start with my blue line. So my blue line has a domain of reals, but it's got a range of only -4 to infinity. And that's because the very bottom bit, the very lowest point on the graph, has a y value of -4. For the purple line, the domain of the inverse, well, that's going to be the old range. That's going to be -4 to infinity. And we can see that because the least x value is -4. The range, however, is going to be reals, because we've swapped our x and y. So the reason why this is quite wordy and mentions whether the relations are functions is because this kind of question cannot just say, find the inverse function. The inverse function doesn't exist because the original y was not one-to-one. We're now going to look at what is virtually the same question. We're being told to consider this graph. So this graph here is y equals x squared minus 2x minus 3. Now, we can already use everything we know about it, so we'll just box it off and remind ourselves that we can use that. This time though, we're being told that the domain is restricted to -infinity to a. Now it's telling me that a is the largest possible value such that the inverse function exists. This is a very common way that the exams in VCE methods will ask you to just find the largest domain. If it's a quadratic, this always means restrict at the turning point. So you may recall from a moment ago that x of the turning point was equal to -b on 2a, and that worked out to be 1. So if I'm considering this graph of the parabola, and I need the domain that's all the way to the left, that's at -infinity, and it goes up to a, then my domain, x is an element of -infinity to 1. So that gives my value of a as the largest possible value such that the inverse function exists. Now we'll draw a quick graph and I'll explain why. Remembering that parabola from last time, it looked a little bit like this. And if I restrict at the turning point, then I'm getting rid of everything on the right. Now, why is this the largest possible domain? Well, imagine that I just restricted it up here. This is also 1-to-1. I could restrict it here too, which is also 1-to-1. So it's important when we talk about a quadratic being restricted for the largest possible domain, such that it's a 1-to-1 function, such that the inverse exists, then we need to restrict at the turning point. So that's going to be 1, -4. And we worked that out in the last video. So part A was to determine the value of A, and in this case I would say A equals 1. Part B is to sketch the restricted graph of y and its inverse on the same set of axes. Well, if I think back to my previous graph, I had 0, -3 and -1, 0. So the inverse graph will now have 0, negative 1. So now my inverse has to swap those two around. So that will be 0, negative 1. The 0, negative 3 will become negative 3 and 0. And the 1, negative 4 will become negative 4, 1. Now, if I join these dots, we can see that we have that bottom half of the graph that we looked at last time. If we think about where is this reflected, it's reflected about the line y equals x. So we've got almost all the critical points. The only thing we're missing is that point of intersection right there. We can find this by letting x squared minus 2x minus 3 equal x. So to solve for this, I will subtract x from both sides. So I've got x squared minus 3x minus 3 is equal to 0. I can make use of the quadratic formula to say that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. That gives me 3 plus or minus the square root of 9 plus 12 all over 2, which is 3 plus or minus root 21 on 2. Now, because I can see that it's down the bottom, I'm going to take the negative here. And the point of intersection is 3 minus root 21 on 2. The y value is going to be the same. This will always be true because it needs to also be on the line y equals x. So you're always going to get a repeat for this point of intersection. It's asked for the domain and range of both graphs. Well, here, the domain of y is equal to, it's in the question, negative infinity to a. The range of y is equal to negative 4 to infinity. For my inverse function, we swap these around. The domain of the inverse is equal to negative 4 to infinity, and the range of the inverse is equal to negative infinity to 1. This is a good time for you to pause the video and try this problem on your own. Now, we're going to make a slight adjustment. We're being asked first to sketch the graph of f, and this is the function of f. We're being told that the domain is from 3 to infinity, and remember that that maps onto reals. That's not the range, it's just saying the output is going to be a continuous line. The output could possibly be all real numbers. Now, I'm going to tell you, let's not worry about finding the inverse function. The purpose of this video is more about sketching. It's more about looking at graphical methods for sketching the inverse. We'll do that in the next video where we physically find the inverse algebraically. So we're being asked to sketch this graph, and also we're being asked to sketch the graph of the inverse f. It's important that we do this on the same set of axes. So try this problem on your own. You can pause the video and we'll do the solution in a moment. So let's start with f. F has an endpoint of 3. And if I plug that into that equation, f of 3 is equal to the square root of 3 minus 3, which is 0. So my endpoint is 3, 0. You may also recognize that using your understanding of transformations. So if we draw up our axes, and we'll give ourselves a little bit of room to do this, we can start at our endpoint, which is 3, 0. And this is a positive square root function, so it'll just do that. Now I don't have any other critical point, so I might just find one. If I subbed in the value 4, so if I had f of 4, that would be the square root of 4 minus 3, which is 1. So I know I've also got this point, 4, 1. Now the reason for me doing that is simply because if I'm trying to sketch the inverse function, I want some points that I can swap around. The idea of 3, 0 should now become 0, 3. So that's going to be up here. The old point 4, 1 will become 1, 4. So that's going to be 1, 4, which is there. So that helps me with my general shape. If we're still unsure of this shape, we can try sub in another point that we know. For instance, if we subbed in the value 12, f of 12 is equal to 12 minus 3, which is the square root of 9, which is 3. So all the way at the end here, if we keep this line going, we can think that we've got 12, 3. Now, my new point from 12, 3 will become 3, 12. So you can think that this is actually arching up. There's my 3, 12, there's my 1, 4, and so the curve actually looks like that. We can just tidy it up by putting in a point that exists on the line, like that. And so I can see that there actually is no point of intersection here. And if I think about my graph y equals x, which is that 45-degree angle, then you can see that there's no wonder that there's no intersection. It's because these graphs never touch. The final part is to label everything. So I've got an x-axis, a y-axis, this is y equals f of x, and this is y equals the inverse of x. Let's once again pause the video and see how you go at this question here. We're being told that we have a function f. Now, f has got a domain, which is 1 to 5. And it is also a square root function that's going to look something like that. We're asked to sketch the graph, so that's what my question's telling me to do. Sketch the graph of f of x and the inverse of x. And it also says that I need to do it on the following axes, so they have to be both on the same axes. It's after me giving the domain and range for each. Now I can usually notice this because it's worth 3 marks. If this was just asking me to sketch a graph, it'd be worth 2 marks. And that's usually the way that these exams work. So pause the video, give this a go, and we'll do the solution in a moment. So I'm hoping you've given it a go yourself, and let's try the first graph. F of x is equal to the square root of x minus 1 plus 3. So the end point is 1, 3, and it's going to shoot off that way. So I've got 1, and I've got 3, and I know that it's going to do that. So here's my point 1, 3. When I'm given a scale, I should try to use it. And I think I might just extend this line out a little bit to make sure of my shape. I know that my inverse function will reflect about this graph. And so if I flip that over the ruler, imagine that I've done this, and I've said y equals x, you can see that there is in fact a point of intersection here. So how do I go about it? Well, for the inverse, 1, 3 would become 3, 1. So 3 1's down here. And that actually gives me enough for my shape. So the last question is, how do I get that point of intersection? Well, I can find the point of intersection by letting f of x equal x. So the square root of x minus 1 plus 3 equals x. If I bring the 3 over, the square root of x minus 1 equals x minus 3. And if I now square both sides, then x minus 1 equals x minus 3 squared. Let's try and give ourselves a little bit more room to solve this. X minus 1 equals x squared minus 6x plus 9, because that's x minus 3 all squared. If I bring everything to the right, x squared minus 7x plus 8 is equal to 0. And the factors of 8 that add up to negative 7 are going to not actually exist. It would be a good time once again to bust out the quadratic formula. X is equal to 7 plus or minus the square root of 49 minus 4ac all over 2a. So that is 7 plus or minus the square root of 49 minus 32. So that's going to be the square root of 17 all over 2. Well, I know that this has to be plus because I can see it physically, it's a positive number. So I'll say that it's 7 plus root 17 on 2. That makes my point of intersection 7 plus root 17 on 2 and 7 plus root 17 on 2, because remember this occurs on y equals x. Every x is the same value for y. So that's enough for 2 marks, but now I need to give the domain and range for each. So I'll say that this is y equals f of x, and this is y equals the inverse of f. And so that my domain for f is going to be 1 to infinity. My range for f is going to be the lowest y value, which is 3, to infinity. Well, these need to swap for my inverse. So the domain of the inverse is equal to 3 to infinity. The range for the inverse is equal to 1 to infinity. And we can see this because the lowest x value is 3, so that's where that comes from. The lowest y value is 1, that's where that comes from. Our final question is also quite a common one. We're asked to find a maximal domain for this thing here such that the inverse function exists. Well, another way of saying such that the inverse function exists is to say so that it is 1 to 1. Well, remember that means restrict at the turning point. So if y equals 3x squared minus 2x plus 4, the axis of symmetry is negative b over 2a. So that's just going to be 2 over 6, or 1/3. The maximal domain, the domain of x, could be equal to, or let's say rather the domain of y, I mean to say, could be equal to negative infinity to 1/3, or it could be 1/3 to infinity. Either one of these answers would be correct. So in summary, what we need to remember is that when we're saying swap x and y, we're really saying every single coordinate swaps its x and y. When we're sketching a graph of an inverse, we need to reflect along the line y equals x, which of course is just that leading diagonal at 45 degrees. This could be represented a number of ways. It could either be in functional notation, or as a transformation matrix.